present in a particular ion. In the past, we've learned that the number of electrons is equal to the atomic number. And this is what's shown on your periodic table. This is true for atoms. Atoms, by definition, are neutral. This means that the positives, the protons, balance out the negatives, the electrons. So in a neutral atom, there are the same number of positives as negatives, so the number of protons and electrons are the same. This is not going to always be true for something called an ion. An ion has an extra charge, and it might be an extra positive or it might be an extra negative. So it's worth asking ourselves, how should we visualize an atom and its electrons? No one's ever actually been able to see the specific parts, like we can't see a proton or a neutron or an electron, even with our very most powerful microscopes. So we have to think about how we create a visual model. One model that's common is the electron cloud model. What's shown here is an electron cloud model, and each dot represents the likelihood that you would find an electron in that particular space. So what you can see is that there are some places, some areas, that you're more likely to find an electron than others. But at any given point in time, we don't know where the individual electron is. So this model really shows sort of a probability distribution. We can show the same thing using a mathematical model. In this case, r, which is shown across the x-axis, represents the distance from the center of the atom, or the radius from the center of the atom. And the graph, the pink graph, represents the probability that you find an electron at a particular location. So again, we know that there are some places that it's much more likely to find an electron than others. What we can actually see, here is a picture. This is of a nickel atom, and this is an image of its electron cloud. You can see it has this interesting sort of clover leaf shape. And this was taken using something called a scanning tunneling microscope. What it says here is that the central spot is the actual atom itself, surrounded by this clover leaf pattern. And this indicates something about the nature of the pattern that the electrons form in this atom. Perhaps a more useful model to us is this model of electron shells. We picture the nucleus as being like the sun, and the electrons as being like the planets that orbit that sun. We think of those electrons as existing at different orbital levels, or different shells. And this is what we refer to as the Bohr model of the atom. Each shell can only hold a certain number of electrons. So where do those electrons go? Well, we start filling from the inside shells and work our way out. The first shell can hold up to 2 electrons. So that first shell can have no electrons, 1 electron, or 2 electrons. Once it has 2, then it's full and we move to the second shell. That second shell can hold up to 8 electrons, so it can have anywhere from 0 up to 8 electrons. Note that if there are no electrons in a shell, we generally don't describe that shell as being there, so we don't typically talk about empty shells. The third shell can hold up to 18, but what happens is the electrons start spilling over into the fourth shell before that third shell is completely filled up. So once we get past the third shell, we start to see some interesting patterns in how the electrons fill up the shells. In order to predict how they fill up the shells, we'll need a model of where the electrons go that's more advanced than the one we use in 8th grade, but it is the model that you'll learn in high school chemistry. For this year, the electron shells model is going to suffice. So, like we said, each shell can hold up to a certain number of electrons. The electrons fill up the inner shell first until they get past that 8 in the third shell when they start spilling over. So if we were to look at the periodic table and look at the Bohr models of some of the atoms in it, here's a Bohr model of hydrogen. The nucleus here is represented with just that center. We can see that lithium actually starts to spill into the second shell. So it's worth noting that both hydrogen and lithium in this first column have 1 outer shell electron. Beryllium in the next column has 2 outer shell electrons. Boron, and here we're sort of skipping over that middle part of the periodic table where our transition metals are, has 3 outer shell electrons. Carbon has 4, nitrogen has 5, oxygen has 6, fluorine has 7, etc. So what we notice is if we look down the columns in the periodic table, column 1, all of those elements have 1 outer shell electron. Column 2, they all have 2 outer shell electrons. Skip over the transition metals to column 3, they have 3 outer shell electrons. So we want to know what makes atoms happy. Now obviously atoms don't really have emotions, and so what do we mean by happy? Well, in this case, happy is a metaphor for the atoms being stable. And stable means that they are the least likely to combine with other atoms to form new compounds. And they are happy or stable, or not likely to combine with other things, when they have 8 electrons in their outer shell. We refer to the electrons that are in an atom's outermost shell as the valence electrons. For some atoms, the valence electrons will be in the second shell because that's the very outermost shell. For other atoms, the valence electrons might be in the 4th shell or the 5th shell because that's that atom's outermost shell. And again, atoms are stable when they have 8 electrons in their outer shell. And we call this the octet rule. Octet, think octagon, octopus, the rule of 8. When we draw Lewis dot diagrams, what we do is we don't draw the nucleus and all of the inner electrons. All we do is we show the valence electrons spaced equally around the element symbol. So here's an example. This is a Bohr model of an atom that has 8 protons, 8 neutrons, and 8 electrons. If we were to draw the Lewis dot diagram for the same atom, we would replace the nucleus and the inner electrons with the symbol for the element. In this case, the element is oxygen. And then we would take those 6 outer shell electrons and space them evenly around the element symbol. So there's the first 4, 5, and 6. There is a reason that we show them in these little pairs, and it has to do with how this element is going to bond with other elements. So here we're showing the Lewis dot diagram for oxygen. It has a total of 6 valence electrons, and the O represents both the nucleus and the inner shells of electrons. So here are the Lewis dot diagrams, again for some of the items in the periodic table. Now notice if you look down column 1A there, you'll see lithium and sodium. Their Lewis dot diagrams have the same structure. They both have 1 outer shell electron. Even though sodium has a whole bunch more inner shell electrons, we notice that elements in the same column have similar Lewis dot diagrams. Now let's look at what happens when we start to change the number of electrons that an atom has. Remember, an atom is electrically neutral. The number of protons is equal to the number of electrons. When you did math and you learned about integers, a plus chip and a minus chip canceled each other out, and the same is true with electrical charges. The positive charge and the negative charge balance each other out, and so the atom is electrically neutral. Ions, however, are different. Ions are electrically charged. They might have a positive charge or a negative charge. And the way that happens is that the number of protons is not equal to the number of electrons. Shown below is an example of an ion that has 4 protons but only 3 electrons. That ion would have a net positive charge. 3 of the pluses would cancel out with 3 of the minuses, and that would leave us 1 leftover positive charge. So that would result in a positively charged ion. If we had more negatives, we'd end up with a negatively charged ion. So if you add or take away electrons from a neutral atom, what you get is called an ion. And it's either a positive ion if it has extra pluses, or a negative ion if it has extra negatives. The oxidation number of an element tells you how many extra pluses or minuses that happy ion has. What does happy mean? Well, remember, happy was an analogy for an atom that is stable, that has 8 outer shell electrons. So to get to having 8 outer shell electrons, it might have to gain some electrons or lose some electrons. So let's look at how we find the charge of an ion. Above is shown a lithium atom. It's electrically neutral. It has 3 protons and 3 electrons. On the bottom, we see a lithium ion. This ion has had one of its electrons taken away. We lost a negative charge, so what it's left with is 3 protons that are positive, but only 2 electrons that are negative. The positives are greater than the negatives by 1. So this has a +1 charge. Notice in this case that when you take away an electron, you get a positive charge. A common mistake is to have that idea backwards, that taking away an electron should give a negative charge, but in fact that's not the case. If an atom loses an electron, it makes a positive ion. But if an atom gains an electron, it makes a negative ion. Remember, those electrons are negative. If they bring their negative charges to the atom becomes a negative ion.